You've probably heard of electric fields, gravitational fields, and magnetic fields. For example, you might have seen a description of the electric field during a lightning storm or the magnetic field of a magnet. But what exactly is a field? Is a field the same as a force? This video explores fields and builds upon what you already know. After completing this assignment, you should be able to describe the relationship between an electric force and the electric field. Estimate the relative strength and direction of the electric field due to a charge distribution, and describe the direction and relative strength of the electric field using electric field line diagrams. Getting the most out of this video requires a solid understanding of electric forces, charged particles, and Coulomb's law. Understanding electric fields is important because many phenomena that you encounter every day involve electric fields. For example, electric fields are central to understanding how common electronic devices work. Consider a point-like object A having a positive charge Q. If another point-like object B, having a positive charge Q0, is nearby, object A exerts an electric force on object B. How does object A exert a force on object B without touching it? We envision that object A produces an electric field throughout space. This electric field exerts an electric force on object B. This force is the product of the electric field vector E, evaluated at location B, and the charge Q0. Now suppose object B has a charge Q0 that is negative, but Q is still positive. In what direction is the electric field due to charge A at location B? The correct answer is that the electric field is directed to the right. Although the force exerted on object B is to the left, since Q0 is negative, the electric field is still directed to the right. How can we determine the electric field of the point-like object A? We can use Coulomb's law to express the force on object B due to A. Since this force is also equal to Q0 times E, we can solve for the electric field. Notice that the electric field at B does not depend on the charge of object B. Increasing Q0 increases the force, but not the electric field. In fact, the electric field at B remains the same even if there isn't a charge at B. What does the electric field due to object A look like at other locations? We can use object B to determine the electric field at other locations. First, find the force exerted on charge B, and then divide this force by Q0. We now show the electric field at a few more locations. Often, we encounter situations containing a distribution of charged particles. For example, suppose there are 4 charged particles. How do we find the total electric field due to all of these particles at some location P? At any location P, each of the point-like charged particles produces its own electric field. The total electric field is simply the vector sum of all the individual fields. As an example, let's look at the electric dipole, consisting of a positive and negative charge, having the same magnitudes, separated by a small distance. In what direction is the electric field at location P? The correct answer is that the electric field is directed down. The total electric field at location P is the sum of the electric field due to the positive charge and the electric field due to the negative charge. Notice that the electric field due to the negative charge points towards this charge. At the location P shown, the two electric field vectors have the same magnitude, and their sum results in a total field pointing straight downward. But if we look at a point closer to the positive charge, the magnitude of the electric field E1 is larger than that due to the negative charge E2. In this case, the total electric field, while still downward, also has a component oriented to the right. Let's move the location P around the dipole to get a feel for what the electric field looks like. Let's include more locations to get a better feel of what the electric field of a dipole looks like. We now introduce a method of visualizing electric fields using field lines. Electric field lines are drawn such that they are everywhere tangent to the direction of the electric field at that point. Electric field lines always originate from positive charges and terminate at negative charges. For example, the electric field lines of a positive charge look like this, and the electric field lines of a negative charge look like this. Notice that the strength of the electric field is related to the density of the field lines. What do the electric field lines for the electric dipole look like? Remember that along any electric field line, the electric field is tangent to the line. Directly between the two charges, we see the electric field is oriented straight down, so one line looks like this. Let's draw in some more lines. Okay, let's recap the key parts of electric fields. We set out to describe the relationship between an electric force and the electric field. Estimate the relative strength and direction of the electric field due to a charge distribution. And describe the direction and relative strength of the electric field using electric field line diagrams. You now know that the force exerted on a charged particle by an electric field is equal to the charge times the electric field, and that the electric field due to a distribution of charges exists throughout space, even in locations that don't contain any charge. We've also seen that the electric field due to several charges is equal to the vector sum of the individual electric fields produced by each charge.